This is lesson 3 in unit 9. We're talking about vector valued functions. In this lesson and in the next lesson, we're going to explore parametric equations where x is a function of time and y is a function of time, and they're continuous functions on some given interval. We're going to use both component form and the I and j form to write our vector valued functions. So depending on what you're familiar with from pre-calculus or from physics, we can write a vector function r of t using the component factors where the x variable is a function of time and the y variable is also a position function in relation to some time. We can also use the I as the unit vector for the horizontal direction and j as the unit vector for the vertical direction. So just whatever you're familiar with. To geometrically represent a vector valued function in two-dimensional space, we could place some vector r as a function of time with its initial position at the origin, that would be here. And then as t varies, the tip of the radius vector r is going to trace out the curve. So you can think of this vector moving along as we go from some point A to some point B on this unit vector, that each one of those vectors traces from the origin along the curve to make this shape r of t. The arrowheads along the curve indicate the orientation of the curve as the values of time increase. So just to get started, let's give some practice here. We want to express the parametric equations. If x is 2 cosine of t and y is t plus the sine of t, we want to be able to write that as a vectored value function. And we can either write it using the component factors where r of t is 2 cosine t and y of t is t plus the sine of t. So using component form, or if you want to use the horizontal, then 2 cosine of t in the I direction, and usually this is a bold variable, and then t plus sine of t in the j direction, which is the vertical. You can also see these with a little hat on them sometimes to indicate that it's a position vector. In example 2, if we're given the vector equation r is this equation, we want to find the x coordinate and the y coordinate. So x would be the t squared plus 1, and y, our x of t is t squared plus 1, and our y of t, excuse me, is natural log of t 2 minus t. Then to find the domain of those that we want to have the overlap, and we know that t squared plus 1 has a domain of all reals, that's just a parabola, and natural log of 2 minus t has a domain where t minus 2 has to be bigger than or equal to 0, so t has to be less than or equal to 2. And like I said, we want the intersection of those components. We want the intersection of the components. So the domain of our function r of t, the domain of r of t, is going to be the overlap from negative infinity to positive 2. So this would be the domain of that vector equation. In example 3, we want to sketch the plane curve represented by 3 cosine t in the horizontal direction and 4 sine t in the vertical direction from 0 to 2 pi, and we want to use arrows to indicate the direction. So we know that r of t is an ellipse. And it's going to be tracing in a counterclockwise direction. Counterclockwise. So 3 cosine t in the horizontal means that we have 3 on the x-axis and then 4 in the vertical and 3 and 4. And we would trace out beginning at 0 around to 2 pi. We would trace out in that counterclockwise. Oh, that's not very good. But we'd put some arrows along the pathway to indicate how the ellipse traced out from 0 to 2 pi. So we can draw or sketch a vector valued function. Here on this next slide, we're just looking at the different operations of vector functions, where you can see if you're adding or subtracting 2 functions, we would combine the horizontal and the vertical, and then we can multiply by a scalar. So we can get the scalar to multiply by each term, and then a dot product is where we multiply the x and y components and then add them together, the x with the x and the y with the y, and add them together to get a scalar. Also taking derivatives and limits and looking at continuity. The limit of a vector function is simply taking the limit in the horizontal direction and the limit in the vertical direction and adding those together. The derivatives are simply taking the first derivative of each component piece. And talking about continuity, a vector valued function is continuous at a point A if the limit at a is the function value at a, and a vector valued function is continuous on an interval provided that the vector function is continuous at every single point in that interval. Okay, in example 4, we're going to add r sub 1 of t and r sub 2 of t. So using component form, our r sub 1 is this t squared here, and then 3t squared minus 1. And then the y values would be 3t minus 2 and 4t. So we're going to add those together, which would give us, 4t squared minus 1 for the x component, or the horizontal direction, and then 7t minus 2 for the y component, or the vertical direction. Then here we have the dot product, so r sub 1 of t dotted with r sub 2 of t, which is our t squared times the 3t squared minus 1, and then we'll add the 3t minus 2 times the 4t. So to dot product, we have the product of the x times the x and the y times the y, or the i'th term times the i'th term and the j'th terms times the j'th term. So in this case, we got 3t to the 4th minus t squared plus 12t squared minus 8t, and combining those together, we have 3t to the 4th plus 11t squared minus 8t. So this is a scalar. This one is a scalar. And then h of t is 2 over t, and we're dotting that with the r sub 1 of t, which is t squared, and then 3t minus 2. So dotting that together, we have 2t squared divided by t, so that's 2t, and then 3t times 2 over t, so that would be 6 minus 4 over t. And in this case, this isn't a dot product, this was just a function and multiplied by 2 vector functions, so that's like scalar multiplication, and we're done there. And then in part D, we want the distance, so the magnitude is going to be the r sub 1, that's t squared minus 3t squared minus 1, and then the y component is 3t minus 2 minus 4t, so the distance is, let's see, this is 1 minus 2t squared, 1 minus 2t squared, quantity squared, and this one would be negative t minus 2 quantity squared, so our magnitude, and expanding this, we're going to have the square root of 4t to the 4th minus 4t squared plus 1 plus t squared plus 4t plus 4. And then combining those terms, we've got the square root of 4t to the 4th minus 3t squared plus 4t plus 5. So we have the magnitude or the distance between those. Here in example 5, we're looking at the limits for our vector functions and finding the limits if they exist. So in this one, simple direct substitution would tell us the limit as t approaches 2 on the x component would be 8, and as t approaches 2 on the y component would be 2 divided by 3. So the limit does exist, and the limit value is this vector. The limit as t goes to pi on cosine would be -1, and on negative sine of pi over 2, that would also be -1. So -1 is our limit at pi on that vector function. And then in this case, we have the I and the j forms, and the limit at e to the 0 is going to be 1 in the horizontal direction or the I direction. And the limit at 0, this is 3 and sine of t over t. You know, think about the special limit property that we learned back in Unit 1. The sine of t over t is 1. And if we pull the 3 out, then this by definition is 1, and 3 times 1 is 3 in the vertical direction or the j component. So 1i plus 3j, or 1 comma 3 if you wrote it in component form. And then this one, the limit at infinity as t goes to infinity on e to the negative t, that would approach 0, and then this is 0 divided by 1, which would also approach 0. So 0 over 0. 0 over 1, and our limit at infinity is 0, 0, so the origin. You could also use L'Hopital's rule on this one if you needed to. In example 6, we want to state the intervals on which the vector valued function is continuous. So, to be continuous on an interval, we have to be continuous at every point on the interval. So I want to consider the domain in the I direction for the square root of t minus 1. That domain would be inclusive from 1 to infinity. And then the domain on the j, we would have to jump over the value at 0. So we wouldn't be continuous at 0, but we would be continuous everywhere except 0. And then for r of t, we want to have the overlap of that. So r of t is continuous on the overlap, which would be from 1 to infinity, including 1. So that would be our interval of continuity. In example B, considering the x component, the domain for the x direction or the horizontal direction would be from -2 to infinity, and the domain on the vertical component would be everywhere continuous except -2 and +2. So we would have to skip over those values where there's division by 0. And then the overlap, r of t is going to be continuous on, let's think about this, from -2 to 2, and from 2 to infinity, because this one overlaps here and here, 2 to infinity. So we're continuous on those two intervals. For example 7, we're given r of t is this vector, and we want to find the derivative. So taking the derivative of each piece, the first x value derivative is 6, and the y value is -5. So we have this vector 6, -5. In part B, r prime of t is going to be 1 over the square root of t in the I direction, and this is going to be 3 over t in the j direction. So our first derivative. And this one we want to find the second derivative, so the first derivative is going to be 3t squared, 6t, and then our second derivative would be 6t and 6. So finding the second derivative. And this one we're going to be given this function, vector function, and we want to find the dot product of the first derivative with the second derivative. So using the first derivative, we're going to have -e to the -t and 2t for the first derivative. The second derivative is going to be +e to the -t and 2. And then coming down here, we want to do r prime dotted with r double prime. So we've got the x component, -e to the -t times e to the -t, and we're going to add 2t times 2, so this is going to be a scalar, and our results will be -e to the -2t plus 4t. So this is our scalar dot product of r prime times r double prime. And finally, the last thing we're going to look at is the derivative rules, and I'll save those for you to muddle through. We've got the constant multiple rule, the sum and difference rule, function and vector multiplication, the product rule for vectors, the product rule for dot product, and then the chain rule. And we'll go through each of these in our last example, along with some integration properties, I believe. So we want to look at, given U and V are continuous on some interval, closed interval from A to B, then the following rules can also be applied for an indefinite integral and for a definite integral. And you can see that we're taking the U component and the V component in the I direction and the J direction, or on a closed interval for a definite integral. Given R, U, and W, and we want to find, in this case, the product rule for dot product. If you look back at the chart, that rule said if you're taking the derivative of U dotted with V, we're going to do U dot V prime plus V dot U prime. So in our case, we're going to do R dotted with U prime plus U dotted with R prime. And first we need to know the R prime of T. So R prime of T is 2T and 0. And then we need the U prime of T, which is 1 over T and negative 1. And then to take the derivative, following this rule that was on the derivative rules, the R function is T squared plus 1. And we're going to multiply that by the U prime, which is 1 over T for the X component and negative 1 for the Y component. So this is the R plus R dotted with U prime. And then we have U dotted with R prime. So U is natural log of T minus T, and we're dotting that with R prime, which is 2T and 0. So we have 2T here and then 0 here. So combining all our like terms, we've got a T minus 1 plus 2T natural log of T and then minus 0. So there's our product rule for the dot product. In part B, we're taking the derivative of W times T. So this is the product rule for vectors. And the product rule for vectors is going to be W U prime plus U W prime. So let's write that out. That's going to be W U prime of T plus U prime U of T W prime. So just like first times derivative of the second plus second times derivative of the first. So it's all pretty familiar. In this case, we need W prime of T, which is 2e to the 2t. And then U prime of T, we already found that in part A, 1 over T and negative 1. And then our W is e to the 2t with our U prime, so 1 over T negative 1, and then 2e to the 2t with our vector natural log of T and negative T for the U. And then putting all of that together, we can factor out e to the 2t as a common factor, and then have 1 over T, and then plus 2 natural log T minus 1 and minus 2t. Oh, mercy. So 1 over t plus 2 natural log of t minus 1 minus 2t. Okay? 2 more to go. In part C, we've got same thing, just different. We've got the derivative of r times w prime plus w dotted with r prime. And our r prime, let's move this down. So our r prime is 2t and 0, and our w prime is 2e to the 2t. And following our rule for the derivative of the product rule, we would have t squared plus 1 times w prime, which is 2e to the 2t, and then w was e to the 2t with r prime, which is 2t and 0, and then combining terms, let's pull out a 2e to the 2t, because we can take this 2 out with this one. So we've got 2e to the 2t and t squared plus 1, and then comma, we need a 1 here. No, t squared plus t for the x with the x, and then that 2t is a 1, and then the 0. Okay, so 2e to the 2t and t squared plus t for our x component and 1 for our y component. And then part D, we're taking r of w of t, so this is the chain rule, and the chain rule is going to be r prime of w and then w prime of t. So r w of t is e to the 2t squared 1, and then 2e to the 2t 0 times 2e to the 2t. So we have 4e to the 4t and 0 for our chain rule of r of w of t. And then our last two examples, we want to find the indefinite integral here. So this one is going to be, let's see, t minus 1 to the half times the 2. So we got a 4/3 t minus 1 to the 3/2 plus a constant. And then this is going to be cosine of t plus another constant. So for part A, this is part A. And then part B, our indefinite integral is, mercy, negative 1/2 e to the negative 2t plus a constant. And then this one's going to be, let's see, that's integration by parts there, isn't it? We need t minus 1. So let's think about this for integration by parts here. So we got 1 over t plus 1 times t minus 1. And our a value is going to be negative 1/2. And our b value is going to be positive 1/2. So we're integrating 1/2 of 1 over t minus 1 minus 1 over t plus 1 dt. So this is going to be natural log, so 1/2 natural log of t minus 1 minus t plus 1, so we can rewrite that as a fraction. And that would be this piece here. So we've got plus 1/2 natural log, absolute value, t minus 1 in the numerator, t plus 1 in the denominator, plus a second constant. So we've got this for our indefinite integral for part B. Here we're going to evaluate the definite integral. So in the first case, we've got t cubed minus 1/2 t squared, evaluated from 0 to 3. And the second one, we have t to the 4th plus 1/2 t squared, evaluated from 0 to 3. So this vector gives us 27 minus 9/2 for the x component, and 81 plus 9/2 for the y component. So 45/2 and 171/2 for our definite integral. In part B, we've got e to the t power from 0 to pi over 2, and this one is going to be minus 1/2 cosine 2t from 0 to pi over 2. So here we have e to the pi over 2 minus e to the 0 for the x component, and then what we got, -1, so minus -1 from 1 for the y component. In example 11, we want to find the r of t is the integral for cosine sine, given that we've got this initial condition. So r of t is the sine of t plus a constant for the x component, and negative cosine of t plus a constant for the y component. And if we let t equal 0, then the r of 0 is our given 1, -1. So r of 0 is the sine of 0 plus a constant, and the negative cosine of 0 plus a constant. So we have 1 and -1, and c sub 1 is 1, and c sub 2 is going to be 0 for -1 plus 1. So our r of t is going to be the sine of t plus 1 for the x component, and negative cosine of t for the y component. So we found the original function based on the given condition. R of 0 is 1, -1. We solved for c sub 1 and c sub 2 and substituted back in. And here's our last example. If the path of a particle satisfies r prime of t is this vector, and the r of 0 is 1, 4, what is the particle's position at 4? So we could say that the integral of 3t squared 6 radical t with respect to time is going to be t cubed plus c sub 1 and 4t to the 3 halves plus another different constant c sub 2. And if we let t equal 0, the r of 0 is given as 1, 4. So the r of 0 is going to be 0 plus c sub 1 and 0 plus c sub 2, and that has to be 1, 4. So that tells me my c sub 1 is 1 and our c sub 2 is 4. So our r of t is going to be t cubed plus 1 and 4t to the 3/2 plus 4. So we want to know what the r of 4 is. So our r of 4 is going to be 64 plus 1, so 65, and then the square root of 4 cubed times 4 plus 4 is 36. So our location at t equals 4 is that. And I guess you could have done it this way. You could have found that the x is 1 plus the definite integral from 1 to 4 of 3t squared. And then the y coordinate would be the y value 4 plus the accumulation for the 6 square root of t dt. So you could have found those coordinates that way as well. And that's the end of lesson 3.